We are going to look at a few applications of vertical and horizontal asymptotes. Let's look at the formal definition of a vertical asymptote. A vertical line x equals c, where c is just a number, is a vertical asymptote if, as x approaches c, the y approaches either positive infinity or negative infinity. Let's play around with y equals 1 over x minus 3. Now, algebraically, you already know to look for vertical asymptotes by looking at the zeros of the denominator. So I can see that I'll have a vertical asymptote at x equals 3. But I want you to see that numerically and how we go with the definition of asymptote. So what I'm going to do is plug in to my calculator y equals 1 over x minus 3. Then I am going to set up my table set just like I always do. You can start it anywhere, but you need to make sure your independent or your x's are on ask and your dependents are on auto. When I go to my table, I've already entered the values that were in the table. Notice that on 3, the y-coordinate says error. That means that for 3, the fraction winds up not existing because the denominator zeroes out. So that means, and I'm just going to record the values that are on the table. I see that when I plug in 2.9, y is negative 10, and then I get negative 100, negative 1,000. I'm just going exactly with the values that I saw. I'm going to skip. When I plugged in 3.001 on my calculator, I got 1,000, and then 100, and then 10. Now, if you get an error message, then what you're saying is that when I plug in x equals 3, the fraction's undefined, which means the y value does not exist there. That's because at x equals 3, I have a vertical asymptote. But look, as I go toward x equals 3 from the left side or from smaller x values, notice that my y values are getting bigger and bigger and bigger negatively. And so that supports as x goes to 3 from the left, I see my y going to negative infinity. So now, if I look going the other direction, x goes from 3.1 to 3.01 to 3.001. I'm also allowing x to go to 3 this time from the right side, or from x values that are larger than 3. And notice what my y values are doing. They're going from 10 to 100 to 1,000. So my y values are getting huge positively. So as x goes to 3, my y values are going to either negative infinity or positive infinity. It doesn't matter which one they go to. I'm demonstrating a vertical asymptote. Now, a horizontal line, y equals c, is a horizontal asymptote if, as x goes bigger, 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 positively or negatively, y is going to settle down and get closer and closer and closer to some finite number. Well, I know that y equals 2x squared over x squared plus 1. I know that since this fraction is balanced, it's going to have a horizontal asymptote at leading coefficient over leading coefficient, which is 2 over 1, or 2. Now I just want to show you what's going on the t-chart so you can see this numerical progression. So again, I've plugged in y equals 2x squared over x squared plus 1 in my calculator. And I've plugged in the x's from the t-chart. Hey, I noticed that when I plug in 1,000 and 1,000,000, which is 1 times 10 to the 6th, it's gone into scientific notation, it looks like both my y values are 2. That is not true. I want to remind you that sometimes you have to arrow over the y-coordinate to see a more complete readout. So those are not exactly 2, but they're awfully close to it. So again, I'm going to record what I've seen. I'm going to write with skinnier pen here. So what I just picked up off the table, and I'm going to round a little bit here. And then I've got 1.39s and an 8. This one's giving me 1.59s and an 8. And when I plug in a million, I got 1.119s. And an 8. So do you see that my X's are going from 1 to 10 to 1,000 to a million? So I'm obviously letting my X's go bigger and bigger and bigger and bigger quickly. And I didn't have to choose 1 and then 10 and 100. I could have chosen 8 and then 22 and then 374. But the idea to get bigger, bigger, bigger is to go from a 1-digit to a 2-digit to a 3-digit to a 4-digit number. That allows your numbers to get bigger quickly. And I notice that these Y's are constantly getting closer and closer to 2. So I'm showing you a table of values that matches the actual definition of horizontal asymptote. Now let's look at some word problems that work with this. So we have a situation where we have the cost of removing P% of pollutants from smokestack emissions. So if the government decides to add regulations so that smokestack emissions are that much cleaner for the environment, you'll see that it's not that big business owners don't care about the environment, but the cost of making small changes gets really exorbitant. So once again, I'm just going to put the 80,000 P over 100 minus P in for Y in my calculator. So I've loaded the equation in my calculator and I've loaded the X values in my calculator. Remember, when our input is 10%, 20%, 40%, etc., the Y column is printing out the cost of removing that level of percentage of pollutants from smokestack emissions. So we're looking at dollars and cents. So I'm going to go back and I'm going to enter the values that I can see from my calculator. So I see that to remove 10% of smokestack emissions, it's $8,888.89. I'm rounding to 2 decimal places. If I double the cleanliness of the smokestack emissions from 10 to 20%, notice I go from about $9,000 to $20,000. That more than doubles my cost. Well, if I double my percentage again, instead of just going from $20,000 to $40,000, I'm going well over the double price point. So that shoots my price up to $53,000. Now if I double and I get 80% clean air in my smokestack emissions, I'm way more than doubling. So the more perfect the air quality is, the more expensive by far it gets. So now I just want to move from 80 to 90% clean air. That's a $400,000 increase. This is excessive cost for a business. And a business is not just thinking about what their bottom line is, how much money or how much profit they're making. They're also thinking, hey, if the government makes me go from 90 to 92% clean smokestack emissions, that's a $200,000 hit that I'm going to have to absorb, which means I might have to lay off employees. And I think most business owners don't want to have to do that. So there's a little bit more involved in a decision like this beyond just whether I'm care about the environment or whether I just care about profits. There's more going on, because when you run a business, yeah, you want to make profits, but you also want to take care of the people that are working for you. So there's lots and lots of decisions that go into that, lots more going on. But now look at the trend and what's happening. Do you see that my p-value, as I went from 10% all the way up to 96%, I was letting P go toward 100% clean air, because we would all like the air to be perfectly clean. But notice that the y coordinate, the cost, was going just astronomically large. So I'm going to say the y value was going to infinity. Now wait a minute. What does that fall into line with? What's that the definition of? So again, I was going to some x coordinate P, and my cost was just skyrocketing. Hey, I am demonstrating an actual reason that we have vertical asymptotes. I just found out that there's a vertical asymptote at P equals 100. I know that you're not surprised by that, because if I ask you to find the vertical asymptote, you would have said, well, 100 is the x value here, the p value, that makes the bottom zero out. But this is a time when you can see that kind of thing in action, where we actually have a vertical asymptote in a word problem. So now let's switch our focus and let's look at the cost of manufacturing light bulbs for tanning beds. So I'm going to, on this, let's compare the current or the old equipment with the brand spanking new equipment. Because again, if you decide that you're going to actually replace old equipment with new equipment, you need to be real aware of what your average costs are, what you expect your volume of business to be before you jump into something. So it says that we could spend $20,000 to get brand new equipment that more efficiently will produce our light bulbs that we're selling people for tanning bed salons. So I look at it, but it says the new equipment can actually produce the light bulbs at a cost of 75 cents per bulb. So the first thing I do is say, no, wait a minute. That means the total cost of producing B bulbs using the new equipment would be the initial outlay of $20,000 plus an additional 75 cents to run the equipment per bulb. Now, what about the total cost of running my current equipment? Well, it says the old or the current equipment just costs $1.75 per bulb, and I don't have to spend any money on the front end. I've maybe already paid off the equipment that I currently use to produce light bulbs. So the current is just $1.75 times the number of bulbs produced. So what I need to do is compare costs to decide at what point it makes sense to buy the new equipment. So to do that, we need to look at the average cost per bulb. Now, I don't know if you remember that we did an average cost problem back on assignment 10, and we said the average cost is just the total cost divided by the number of items produced. So in the old equipment, the average cost per bulb would be the total cost divided by the number of bulbs produced. Well, that just means that no matter how many bulbs I produce, the average cost per bulb is $1.75 per bulb, period, with the old equipment. With the new equipment, however, let me say average. I'm going to say, well, let me take the total cost, because I do have to absorb the cost of buying the new equipment, and I'm going to divide that by B. Oh, man. That looks like a rational function, That might be why it's in this chapter. So how many bulbs should be produced in order to incur an average cost of $4.75? Now, this means with the new equipment. All right? The old equipment always is $1.75 per bulb. But what I'm going to do is algebraically, I just say, well, if the average cost is $4.75, let's see where that would actually fall. So I'm just going to plug that in for the average cost. Now I notice that if I make 4.75 over 1, it's just a basic proportion. So I'm going to cross multiply. 4.75b equals 1 times the 20,000 plus 0.75b. Well, if I group my b's, I'm just going to get 4b on the left. So that says if I want to bring my average cost down to $4.75 per bulb, then I actually have to produce 4 or 5,000 bulbs. Well, okay, so if I'm only going to manufacture 5,000 bulbs, it makes 0 cents to buy the new equipment, because the cost of the new equipment plus the cost per bulb is making me pay $4.75 per bulb, where if I just stuck with the old equipment, it would only be $1.75 per bulb. So right now, if this is the volume of business I'm doing, it doesn't make sense for me to buy anything new. What if I start exploring, well, what about larger and larger bulb manufacturing? So if I produce 10,000 bulbs, again, I'm just going to plug into my calculator. Of course, your calculator doesn't know that we're using B instead of X, so just plug in X where I've got B's. And then when you go to the table, you're going to insert the 10,000, 20,000. Well, notice what's happening. For 10,000, it looks like the average cost comes down to about $2.75. For 20,000 bulbs, the cost comes down to $1.75. Oh, let's talk about that more in a minute. At 80,000 bulbs produced, that brings your average cost down to $1. When I go to 320,000 bulbs produced, that brings your average cost down to about 81 cents per bulb. And look, I went ahead and plugged in 900,000 and actually 1,500,000 bulbs. That's bringing your cost down to 76 cents. Well, let's explore. And I'm going to fill in the table with the values that we just got. So we said the average cost per bulb is $2.75 with the new equipment producing 10,000 bulbs. Then I dropped to $1.75. Then I dropped to $1.25, $1, 88 cents. And then I think for 320,000, we had about 81 cents. And like I said, even when I got up to around $900,000, I think it was somewhere around 78 cents at that point. So the more and more bulbs you produce, because it spreads out that initial outlay of the $20,000, that winds up having less and less big a hit on your average cost. Now take a look right here. So if I buy the new equipment and I know I'm going to produce about 20,000 bulbs over the life of the new equipment, then it brings the average cost down to $1.75. Well, that matches what the current equipment does. So then you have to decide, well, do I get the new equipment or the old equipment? And that's when other factors come into your decision making. For instance, if you know that fewer and fewer tanning salons are opening because people are more scared about the cancer that they cause, you might be thinking, well, I think my business is probably going to shrink over time, so I'm not going to invest in the new equipment. Or you might say to yourself, well, this old equipment that I have, like, it's breaking down more and more frequently, and it makes sense for me to go ahead and buy the new equipment where I shouldn't have the maintenance or repair costs as frequently. So there's different factors that might play into your decision making. But if you know that you're going to be producing over 20,000 light bulbs, and that brings your cost down to $1.25 or lower, then absolutely purchase the new equipment, because it will take care of itself. The initial $20,000 outlay, that winds up becoming something that's negligible over time. So do you see the progression of what's happening? I have let the number of light bulbs get bigger, bigger, bigger. In fact, on the table before, you saw me take it to 1,500,000. So the number of light bulbs I'm looking at is going to infinity. but it looks like my cost is never, I want to say my average cost. It doesn't seem like it's ever going to go below 75 cents. In fact, if you keep toying around on your calculator, I can see that the average cost seems to be going to 75 cents, which is what was promised. Because remember, the information says the new equipment costs about 75 cents per bulb to produce. Why is that? Well, guys, this is the definition of horizontal asymptote. So I've got a horizontal asymptote at y equals, that's your A of B equals 0.75. And if you look at our total cost, we can see, average cost, not total cost, that sure enough, in this equation, it is a balanced fraction. And if you look at lead coefficient over lead coefficient, I see 0.75b over b reduces to 0.75. So this is just a couple of times that you actually see a real life application of asymptotes.